And yes, the homework will be due for 15. Tomorrow we're going to start lab. We're going to do the synthesis lab. So in preparation for the lab, read the procedure. There are actually 4 complexes. We're not going to do all of them. We're just going to do the first one, the chromium complex. So read through the procedure for that.
It's the first one.
Yeah, just the first one.
Okay.
So tomorrow we're going to have a quiz, a short quiz on chapter 24. So the way it's going to work, we'll use the first part of the lab period for the lab, and then we'll stop and then do 24. But there's a lot more stuff I want to say about lab. So what I'm going to do for tomorrow's lab is I'll probably just talk, and then we'll do the experimental work on Thursday.
Okay.
Do it in one day.
Do you want us to prep our
No.
No.
I'm going to talk about prepping the lab book tomorrow in lab.
There's no chapter 16 in our textbook. At least mine. I don't know if anyone else has that.
That will be yours.
Is it just my book?
Bring it back. You have the flex book. Anybody else have that flex book? Missing chapter 16? Oh no. The entire chapter.
Well, there's a preview book online.
I don't know how that happened.
You're mastering Chem and get it on home.
I know, but I still pay for it. I'll just tell you what it's worth.
That's weird. I don't know. Somebody must have requested it got deleted because the previous version had chapter 16, so that's new for me this semester. I'm not sure who did it. I have another copy, but I don't have an app. Let's see. I'll think about it. All right. Chapter 16 is a tough one because you have multiple things happening. Actually, chapter 16 is not acid-based, acid or base in water. And so, it's a lot more complicated because now we have to deal with different equilibria happening at the same time. Because water has an equilibrium going on there, which we're going to talk about soon. It's called KW. But acids also have an equilibrium. For example, if we have a monoprotic acid, then there's something called Ka. If we have a diprotic acid, then we have 2 equilibria, Ka1 and Ka2. And a triprotic acid has a Ka1, Ka2, and a Ka3. A just stands for acid or acid dissociation.
And photo kind of refers to like the hydrogen ion that's displaced, right?
Yeah.
Okay.
So monoprotic would just be like acetic acid, HCl. Diprotic acid would be like oxalic acid, which has 2 acidic hydrogens. Sulfuric acid has 2 acidic hydrogens. Triprotic would be something like phosphoric acid with 3 acidic hydrogens. And so even with a monoprotic now, we have 2 equilibria we have to deal with, Ka and Kw. And then if we go to diprotic, we have 3, and triprotic, we have 4 equilibria that we have to deal with. And so, in a sense, this chapter is a lot harder because we have multiple reactions occurring. And so, compared to chapter 15, chapter 15 you only had one equilibrium, and that was it. But in another sense, this chapter is easier because the worst it gets is the quadratic. And so you don't have to solve third or fourth or fifth or sixth order equations. Just quadratics. So let's first find out what's going on in water. And so let's look at pure water. At 25 degrees C. So let's just try to visualize what's happening in pure water at 25 degrees C. If we start off with water at 0 degrees C. And then, actually, before I do that, let's talk. Why 25 degrees C? You know, yeah, that's what we call room temperature. Is that what we call standard temperature? No. Normally when we're talking about standard temperature, we're talking about gases. And what's the standard temperature for gas?
22.4?
Not 22.4.
100?
Not 100. Standard temperature for a gas. STP.
273.
273 Kelvin or 0 degrees C. But if you're dealing with an aqueous solution, 0 degrees C is not very convenient because pure water would be frozen solid at 0 degrees C. And so if you have pure water at 0 degrees C, it's just a block of ice. In a block of ice, are the water molecules moving?
Not much. Not much.
Okay, not much means what?
Not enough reaction.
They're moving, but not much? What kind of movement do they have?
Vibrating.
Just vibrational. Do you think there's rotational energy or rotational movement? No. Because in ice, ice has a very open structure, low density. In fact, ice is less dense than liquid water, so it floats. Right? But ice, the structure is open because the water molecules try to maximize the hydrogen bonding interaction and thereby minimize the energy. And so they adopt a certain fixed orientation. The orientation is a very open structure, a very open lattice. Lots of empty or dead space in there. And so it's not very dense. But the water molecules can vibrate, but it's not likely to rotate because in order to rotate, you'd have to break the hydrogen bonding interaction in it. At least, you don't completely break it because to completely break it, you vaporize it. And so they're still stuck together, but it isn't optimized. It isn't the lowest energy configuration. And so likely no rotation. In some solids, there are rotations found. When you have spherical molecules, spherical, those can rotate freely. How about translations? Can water translate from point X1 to point X2?
It's frozen.
No, there's no trans. And so all you have is vibrational. Do you think in a chunk of ice, all the water molecules at 0 degrees C are vibrating at the same energy? No. What would you see instead? More towards the surface? Well, at the surface is 0 degrees C and inside is 0 degrees C. Let's say the interior temperature is 0 and the surface temperature was 0. Are they going to be vibrating at the same?
Because temperature is just an average measurement.
Yeah, right. The average energy at the surface and the average energy inside will be the same. But those are just averages. What we're going to see is there's going to be something called a distribution of vibrational energies in there, which we'll talk about later. Then I warm this up. I warm it up and I break some of the hydrogen bonding interactions, allowing the water molecules to rotate and translate. And we have liquid water. And then I'll warm up the liquid water to 25. So going from 0 to 25 degrees C, what changes in liquid water?
So the hydrogen bond bonding has increased the loss for
I'm sorry?
when you raise it from 0 to 25, it increases the energy, right? So then you get more movement, more molecule, which kind of breaks up the hydrogen bond between each.
Well, the hydrogen bonding is still going to stay intact because the water molecules
Yeah,
are
but-
stuck together.
but
And
it's
so,
much-
since the water molecules are stuck together, we'll say the hydrogen bonding interactions there. But you're right, there's going to be more energy. And so temperature is directly proportional to the average kinetic energy from kinetic molecular theory of gases. And so that holds for liquids and also holds for solids. This is for gases, we just look at translational kinetic energy for ideal gases. For real gases, we'll also look at rotational and vibrational energy. But temperature is a direct measure of the average kinetic energy. But pure water at 25 degrees C, let's say we have some pure water at 25 degrees C, would you expect all the molecules to have equal energy? No. What we're going to see is we're going to see a distribution of energies. And the distribution of energies, we can plot the x-axis, we'll plot kinetic energy here, is K. On the y-axis, what should we plot? What do we plot on the y-axis if we're looking at a distribution of kinetic energy?
Time?
Not time, not temperature, the number of water molecules. We either plot the population or the percent. You know, we normalize the population to 100%. And so it's the number of water molecules. And so when we look at that, there are some water molecules with low kinetic energy, some molecules with high kinetic energy, but the bulk of the water molecules are going to have some kinetic energy around here, and the average will be offset a little bit. And so this average corresponds to the temperature of 25 degrees C. When we look at the high or energy water molecules over here, it turns out that there's a very small fraction of water molecules out here that have enough kinetic energy to break bonds. So if you have these two water molecules out here colliding with each other, you can break bonds and form bonds. In other words, you can have a chemical reaction take place. And so this is kind of the threshold energy or the minimum energy required for reaction between water molecules. What is the reaction between water molecules? Well, if you have two water molecules with high energy colliding, then you're going to break bonds and form new bonds. And so what kind of reaction could take place between two water molecules? Well, one reaction that can take place is a Bronsted acid-base reaction. And so we'll have a proton acceptor, proton donor, and form hydronium and hydroxide. So, what proportion of water molecules can do this? It's just a tiny fraction. A tiny fraction. And so that tiny fraction we could show in two ways. One way we could show it is just a huge arrow in the reverse direction, saying the bulk of them will stay as water molecules, and then just a tiny arrow in the forward direction showing a small amount of reaction in the forward direction. That's one way we could show this. And so these uneven arrows, what they're trying to show is that this reaction is heavily biased in the reverse. In other words, the reactants are heavily favored over the products. And so we don't expect to form much product here. In fact, at 25 degrees C, if you have 1 billion water molecules, do you know how many out here? The population is 1 billion. And out here, there's about 4. 4 out of 1 billion will react. This actually, the population here is more, but there's more than just energy. You have to have the correct orientation as well. All right, so this we call the autoionization of water. And so as these water molecules react, shouldn't we just build higher and higher concentrations of hydronium and hydroxide? Well, what's going to happen is as the concentration of hydronium and hydroxide increase, so does the probability of the reverse reaction. And if we look at hydronium is a strong acid, hydroxide is a strong base. And so what happens is this population can't build up too high because eventually, as the population increases of hydronium and hydroxide, that is, then the likelihood of the reverse reaction increases, and pretty soon we'll hit a concentration of hydronium and hydroxide where the rate of reverse reaction is equal to the rate of the forward reaction, and then we reach the set state of dynamic equilibrium. Okay, these arrows here are meant to represent rates. If the arrows were meant to represent rates, then I'd have equal size of arrows. Because once we hit equilibrium, then the forward reaction and the reverse reaction are happening at the same rate, so that there's no net change in the concentrations over here, even though there's constant cycling of water molecules in this process. So I want to know how much hydronium and hydroxide form. So I start off initial, and then there's going to be some change, and then I'll have some equilibrium. This is our standard setup from 1B. Initial, what I'm going to do is I'm going to just reset this. Now I don't know how much here. And so what I'll do is I'll reset all the atoms to the left, keep this at 0 molar and 0 molar. And then I'll let the collisions happen. This is just a process to make the calculation easier. I let the collisions happen, and then I'll see what the change is. The change is I'm going to generate X molar here, so at equilibrium we're going to have X molar and X molar hydronium and hydroxide. And then to solve for X, typically I use K, K value here. But that's one way. But, how was K determined in the first place? In order to determine K, what are the ways that you can determine what K is? How many of the ways one can determine the K value for a given reaction?
It's usually given.
You could look it up in the book, but where did those values from the book come from?
Experiments.
Experiments. So we can measure the what? Experimentally.
Concentration.
At equilibrium. We measure the equilibrium concentrations and then plug it into the K.
Formula, ideal.
Yeah, and then calculate the number. Or we could look up. Well, this one, we could do an experiment. The experiment that we could do is a pH measurement. Do you know what pH measures? So we'll stick a pH probe into our water and we'll measure the pH. pH measures the concentration of hydronium directly. And so the pH is, for pure water, should be 7. And stick our pH probe in there at 7.00. If you tried this with tap water or DI water last semester, it didn't come out 7 because it was not pure, it was contaminated. You recall what the contaminant was?
CO2.
CO2, right. CO2 is going to lower the pH here. But let's say this is pure, non-contaminated, we get a pH 7. pH, P is a power function. Actually, we should say it's a negative power function because it's just the negative power of the hydrogen ion concentration. And so the pH, the equation for pH is the negative log of the hydronium ion concentration. And the pH itself is when we calculate the hydronium ion concentration, the pH turns out to be the negative power the concentration here. And so doing this, we got 10 to the minus 7.00 molar. Now power functions are kind of funny because of what we do with the sig figs. How many sig figs does 7.00 have? 3. It should have 3, but in power function, this counts as only 2 sig figs. Anything after the decimal is significant. Anything preceding the decimal is not significant, because the number preceding the decimal is what we call a placeholder, decimal placeholder. And so actually this number is this. It's 1.0, that gives us our 2 sig figs here, times 10 to the minus 7. Now this 7 is just a placeholder because we can lose this part of it and just write 0.0000, so I need 5 zeros and a 1 0. And so it was just 1, 2, 3, 4, 5, 6. Oops, I need 6 zeros. Sorry. 7. That's where the 7 comes from. You move it over 7 places. Right. And so this is just a placeholder. And therefore it's not significant. And so it turns out that our molarity is 1.0 times 10 to the minus 7 molar based on the pH calculation. So this comes from experiment. X here, sorry, is 1.0 times 10 to the minus 7 molar hydronium at equilibrium, and 1.0 times 10 to the minus 7 molar hydroxide at equilibrium. And so once we have the equilibrium concentrations, we can calculate what K is. K for this is called KW. W stands for water. It's water autoionization. And KW is going to equal the hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium. Which is 1.0 times 10 to the minus 7. We don't use units here. 1.0 times 10 to the minus 7. Since, K's are based on activities, which are dimensionless. Which gives us 1.0 times 10 to the minus 14. K's are valid at specific temperatures, so this is valid at 25 degrees C. But what will happen if I change the temperature? What will happen to K? Well, in order to answer that, let's take a look at what's going to happen to the hydronium ion concentration. Let's say I increase the temperature. Will the pH of water change? Let's say I have water at 25 degrees C. I decide I'm going to warm it up. I'm going to go to 30 degrees C. And so water, pure water at 30 degrees C, is its pH still going to be 7? Or will its pH have changed? This is a trick question.
It'll be more acidic
It'll be more acidic? Why?
because you're boiling off the hydroxide or hydroxide.
It'll become more acidic. Will water become more acidic at 30 degrees C?
Well, not hydroxide.
Like boiling water would be quite acidic then if it's quite a bit higher temperature. Maybe if I cool it down, would it make it more basic? It's a trick question because you really have to know the definition of pH, and you really have to know the definition of neutral versus acidic versus basic. And so this isn't always so clear. In other words, will the pH change? If I change the temperature, will the pH change?
No.
No, the pH is going to stay the same?
Yeah. Yes.
Yes?
Yeah.
Will the hydronium ion concentration change? If I change the temperature, will the hydronium ion concentration change?
No.
No?
No.
Yes?
That could. but-
Okay, let's take one more step back. Maybe we should look at this. Let's look at this. You know, I have some average kinetic energy, this which we call E bar K, right? E bar K, which corresponds to this temperature at 25 degrees C. And so if I increase the temperature, what happens to the average kinetic energy? It increases. If it increases, what happens to the distribution? It shifts. It shifts to the right. And so if this distribution shifts to the right, what's that going to do to the population here? It increases the population here. If it increases the population here, then we're going to get more reaction or less reaction? More reaction. So if I increase the temperature, I expect more collisions. More collisions means more reaction. More reaction means more hydronium. More hydronium means, now this is why it's the negative power, because more hydronium means higher pH or lower pH? Lower pH. Lower pH means more acidic or less acidic?
More acidic.
More acidic. So if I increase the temperature, the pH of water should become more acidic. Is that right? So what's wrong?
Maybe because
You're not accounting for the hydroxide.
Yes. And that's this is why we don't. Yes, the pH becomes lower, but it does not become more acidic. It stays neutral because of how we define neutrality. You know, water is pH neutral. pH neutral means that the hydronium, no matter what it is equal to the hydroxide. And so even though the hydronium increased because more collisions, the hydroxide also increased because we produce them in a 1-to-1 mole ratio, right? For every 2 water molecules, we need to generate 1 hydronium and 1 hydroxide. You can't generate more hydronium than hydroxide. It's a 1-to-1. And so this is what we mean. So yes, the pH does drop, but it doesn't become more acidic. It stays pH neutral. And so this is why pH can be tricky, because since it stays neutral, and since everybody knows pH 7 is neutral, then modern pH meters have an automatic temperature calibration. And that is, you know, the temperature in lab, does it stay 25 degrees C the whole time? No, it fluctuates, right? And as the temperature fluctuates, do you want your pH fluctuating and then you have to rethink all your pH numbers? No, you don't want that. And so what you do is, as the temperature fluctuates and the pH actually does change, the electronics in the pH meter just compensate and then calls it pH 7. So no matter what the temperature is, it's going to read pH 7, so you don't have to fiddle around and do a temperature correction for all your pH readings. Old pH meters have a manual knob. You know, as the temperature changes, you just twist the knob to adjust the temperature. So it automatically recalibrates or resets or normalizes it so that water is always pH 7 no matter the temperature. But is that really what's happening here? No, what's really happening here is as the temperature increases, the pH does indeed change. So, are you okay with this? So what are we going to do in our calculations? Do we have an electronic adjuster that resets the pH each time the temperature changes? Temperature changes, pH wants to change, but it sets it to 7. We don't have that, and so when we do our calculations, we're just going to calculate it as we expect. You know, there's collision. What's the collision going to result in? It's going to result in these numbers. We're going to just take take the numbers as it. All right, this is KW. KW is an important number, so memorize this number. It's an easy number to memorize because people use it over and over so much. It's like the idea of the asphalt. It's hard to forget. All right, if we're dealing with just water, pure water, it's not difficult, you know. But what happens when you put an acid in the water? And so let's look at an acid in water. And the example we're going to look at is, let's go with 0.100 molar HCl, AQ. We have 0.100 mol HCl, so we got HCl dissolved in water. And there are two approaches that one can take with this, because, you know, two approaches is we could do a Le Chatelier's type approach, or we could do a reset, the initial. This is harder. This is easier. But we're going to do it both ways. Let's see. If we do Le Chatelier's, then what we know is we have some water at equilibrium. And so the water at equilibrium, initial at equilibrium will be 1.0 times 10 to the minus 7 molar hydronium and 1.0 times 10 to the minus 7 molar hydroxide. And we generate these concentrations from the collisions of the water molecules. And as those collisions build up again, the concentration of the product builds up, and then we hit this point. Once we hit this point, then we know that the rate of the reverse reaction is equal to the rate of the forward reaction, and there's no further buildup of product. We've reached this steady state. All right, now we're going to perturb this by adding the acid. And we're going to just assume no solution dilution. Normally when you add acid to water, right, you add acid to water, you're diluting it. And if you're diluting it, the concentration is changing. But here I want to keep the calculation simple. And so we're going to add the HCl. And HCl is going to contribute how much hydronium to this? So it's 0.100 molar HCl, so it should contribute 0.100 molar hydronium. And so I'll just say plus 0.100 molar hydronium. This is like Le Chatelier's principle. Will it contribute any hydroxide? No. There's no hydroxide in HCl. And so in Le Chatelier's principle, if I perturb the equilibrium by adding more product or reactant, there's going to be a shift to reestablish equilibrium. And so here I added some product. Now I have too much product. The equilibrium's been upset. There should be a shift. And so let's determine the new initial, the perturbed initial conditions. So we'll do that over here. The perturbed initial is now I have this. I'm going to have 1.0 times 10 to the minus 7 and 0.100. So I'll have 0.100 sub 1, 2, 3, 4, 5, 6, 1 molar. So it just dumped in a whole bunch more hydronium. And then the hydroxide is 1.0 times 10 to the minus 7 molar. And so now my Q is going to be way too big. And there should be a shift. So I add product, it shifts back to the left, that is consume product, and make more reactant. The reactants in this case, just pure liquids. What do we do with pure liquids in equilibrium? Do we even consider it pure liquids? No, because the activity just doesn't change. And so this is why over here in the ice table, you notice I didn't even bother with liquid-liquid. I'm just looking at the AQs. And so you could write a line through these. And so at equilibrium, my new equilibrium is going to be 0.100 sub 0001 minus x molar, and 1.0 times 10 to the minus 7 minus x molar. I know what my Kw is, and so I'll plug these values in here and then solve for x. When I solve for x, I'm going to get a quadratic, right? Second order equation. But there's some tricks you can use. For example, the simplifying assumption. Would the simplifying assumption work in this problem? That is, if we assume x is very small compared to the initial, would it work? So if we assume x is very small, the x would drop out here, right? And we assume x is very small, the x would drop out here. And then we try to solve for x by plugging in up here. But the problem is
then you don't have any x.
yeah, we don't have any x because we just dropped it out of both expressions. So we can't use the simplifying assumption. We got to use the quadratic. And so we'll just solve for x. I said the reset is easier. Let's see. And so I'll let you finish this one if you want. The difference between the reset and the Le Chatelier's is this. Rather than starting with the water at equilibrium, I'm going to start the water at 0. In other words, what I'm going to do is, initial from water, I'm going to say there's nothing there because I'm just going to push all the atoms to the left. It doesn't matter because I'm going to reach the same equilibrium whether I have atoms there or not because I'm not changing the total number of atoms. And so this is just like the water tank. If you have 100 gallons, and it doesn't matter if you put all 100 gallons on the left or all 100 gallons on the right, you're going to reach the same equilibrium. The only thing that will screw that up is if you start removing or adding water, which we aren't. When we're doing this reset, I'm not adding or removing atoms. All the atoms are staying put. And so this is the initial from the water. And then we have the initial from the HCl. The initial from the HCl is going to be 0.100 molar hydronium and 0 molar hydroxide, since HCl doesn't contribute any hydroxide. And so now I'm going to have my reset initial, what I call the reset initial. The reset initial is just 0.100 molar hydronium and 0 molar hydroxide. And getting more zeros in your initial condition means fewer binomials you have to worry about later, making the math easier. But not only does it make the math easier, you'll see one other advantage of resetting it shortly. And so the change here, well, which way? Is it going to be minus x? Yep.
Plus x.
It's got to be plus x because we have 0, and we can't go below 0, so it's going to be plus. We've got 0.100 plus x and x molar. And so in the previous, when we did the Le Chatelier's, we end up with 2 binomials here, and we have to multiply out the 2 binomials to get it into quadratic form. If we do the reset, you'll see that the math is going to be a little easier. Because now, when we plug it into our Kw, which is the hydronium at equilibrium, which is 0.100 plus x, times the hydroxide at equilibrium, which is just x. That looks a lot easier, doesn't it? Yeah, a lot easier. It's a lot less time. 1.0 times 10 minus 14. But there's one other potential advantage to this. And the other advantage is the simplifying assumption. Do you think the simplifying assumption is likely to work here?
No.
No?
Then you remove the x again.
You'd remove the x, but this is it. The simplifying assumption would say that the x is small compared to your initial. And so if you say 0.100 is like a swimming pool, and you add a drop of water to your swimming pool, then that's not significant, and so the x drops out here, and you're left with 0.100. But over here, this is like a parched earth. If you add a drop of water to parched earth, then is that significant?
Yeah.
Yeah. And so here it doesn't drop out. And so only one of these two x's drop out. It's this one. Because x relative to 0.100 can be insignificant, but x relative to 0, anything relative to 0 is significant. So this x will not drop out. And so the other potential advantage here is the simplifying assumption might work. Now, that is only if x is small, but you know, I kind of have an idea that x is small here. Do you know why? I'm
KW
thinking.
is less than 1.
KW is like
KW is
negative
less
14
than
power.
one.
Yeah, 10 to the minus 14, which means the products are heavily favored or the reactants are heavily favored?
Yeah.
Reactants, and 10 to the minus 14 means they're hugely favored. And so if the reactants are hugely favored, we expect very little forward reaction. And therefore, this I expect to be small compared to 0.100. Not compared to 0, because anything significant might be 0. And so we'll try the SA. You know, when we try the simplifying assumption, we're saying that x is going to be much smaller than 0.100. And therefore, 0.100 plus x is just 0.100. And then x relative to 0, again, that doesn't drop out. And therefore, x is equal to 0.1. It's going to be 1.0 times 10 to the minus 13. I didn't even need a calculator for that. Do you see here, the math compared to Le Chatelier's is a lot easier in the reset. But we don't know if it's valid. How do we justify our simplifying assumption? We calculate the percent change. The percent change is the change, in this case 10 to the minus 13, over the initial. Initial is 10 to the minus 1 times 10 squared percent. And so this would be 10 to the minus 10. So this is a 10 to the minus 10% change. 10 to the minus 10% is like nothing. Right? What's our limit? The maximum? 5%. This is way below 5%. You know, this is why I didn't even bother multiplying up the coefficient. And so it's okay. In fact, when you see a percent change like this,
Where'd you get the 10 to the minus 1?
oh, the initial
Okay.
minus 1. I just put everything in exponential form to do a calculation usually. But what I'm saying is, when you see a small percent change like this, a small percent change like this means that even if you solve the quadratic equation, you would have gotten the exact same x. And so you can prove this to yourself. You solve the quadratic without making the simplifying assumption, and you calculate x. X comes out to 1 times 10 to the minus 13, the same number. And so here it's totally justified. There's no problem with using a simplifying assumption, and in fact it saves you time because you would have gotten the same answer as the quadratic. But when the percent change grows and gets closer to 5%, you know, let's say the percent change is 4.9%, or cutoff is 5%, you say it's okay, but in reality, if you use a quadratic, you'd get a better answer. It's just if you're pressed for time, you would do it. And so, here. Good. All right, so let's go ahead and calculate it. This is going to come out to 0.100 plus, now it's 10 to the minus 13. So 10 to the minus 13 means I need 12 zeros after the decimal. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then a 1, 0. So let's add some zeros to this other term here. And so this is going to come out to 0.100 sub 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 1, 2, 3, 1, 2, 3. 3, 6, 9. Now, did adding this little bit here really change my point 100? No. And so this is a good analogy. This would be like adding a drop to, let's say, a lake rather than a swimming pool. It's not really going to change the volume significantly. But what about over here? Is 10 to the minus 13 close enough to 0? What is 0 in... is 10 to the minus 13 close enough to 0? What's another way of saying 0?
Nothing.
Using 10 to the minus what? 10 to the minus what is close to 0?
Minus infinity?
Yes, 10 to the minus infinity is close to 0. So is 13 close to infinity?
No.
No, not even close, right? And so 10 to the minus 13 is significant relative to 0. And so this is equal to 1.0 times 10 to the minus 13 molar. And we never drop that because that's significant. And so now we'll check it. How do we check our answer? We plug the equilibrium concentrations that we just calculated back into K and see if it equals KW. What was KW, the number? 1.0. How many sig figs is that good to? 2. So the 2 sig figs you should know, 1.0 times 10 to the minus 14. Now let's check it. So take this and multiply with this, and what do you get?
1.0 times 10 to the negative 14.
1.0, how about 1.00?
Oh, yeah, right.
1.000
That's just 2 zeros.
times 10 to the negative 14. And so it's good. Good. And so these look like the equilibrium concentration. What's the pH of this?
7.
The pH is not 7. The pH is going to be the negative log. In fact, technically the pH is this. When we do the pH, because the pH is the negative log of the hydronium ion concentration, but we want to be a little bit more specific. We're going to say that the pH is the negative log of the total hydronium ion concentration because hydronium actually comes from 2 sources. Even though this is this is pure 0.100 molar HCl. And so you wouldn't think there are 2 sources of hydronium, but there are actually 2 sources. The 2 sources of hydronium are what? So this is the hydronium that comes from what? The hydrochloric acid. How much hydronium came from the hydrochloric acid? 100. And so we have the hydronium from the hydrochloric plus the hydronium that comes from the water. Can you stop the hydronium that comes from water?
No.
No, you can't. But isn't the hydronium that comes from water 10 to the minus 7 molar? Isn't this problem a lot easier? The hydronium from hydrochloric is 10 to the minus 1 molar, 0.1 molar, right? And the hydronium that comes from water should be 10 to the minus 7 molar. Didn't we just calculate 10 to the minus 7 molar or determine that in the past, in the previous problem? Right? But we didn't get 10 to the minus 7 molar. We got how much? The hydronium from water came out, which is the X, right? The hydronium from water came out to, not 10 to the minus 7 molar, it came out to 10 to the minus 13 molar. And so my question is this. Why isn't it 10 to the minus 7 molar? Shouldn't it be? Because I told you, we have a certain fraction in the distribution that react. Did I change the temperature? No, so I have the same, if I didn't change the temperature, I should have the same number of collisions occurring. Nothing changed with that. But now all of a sudden, rather than getting 10 to the minus 7 molar, I get 10 to the minus 13 molar. Somebody tell me why that is.
Because you dropped the X.
Yeah, maybe because I made the simplifying assumption, you know, experimental error. Experimental error usually works for most things.
Shift in equilibrium.
What do you think? Okay, shift in equilibrium with the hydrochloric, yeah. Actually, I do. I have the same number of collisions happening right in the forward direction because it's at 25 degrees C. The problem is this. Now all of a sudden things have changed. You know, I had the same number of collisions which generated 10 to the minus 7 molar and 10 to the minus 7 molar. And then I got the forward rate equals the reverse rate, and I get a state of dynamic equilibrium. But you know what's changed? What's changed is the rate of the reverse reaction. The rate of the reverse reaction has changed. Now it's much, much faster. Now the reverse reaction is much, much faster, and so the forward reaction can never build up to that same because the reverse reaction will come back and take it out. And so the one way to visualize this is like this. In pure water, you have the hydronium and the hydroxide, 10 to the minus 7, 10 to the minus 7. Sometimes they find each other, collide, and go back to water, right? But now this is totally different because now you have lots of hydronium. And so this is like predators and prey. Let's say the hydroxide's the prey, the hydronium's the predator. And so back in pure water, we had 10 to the minus 10, 10 to the minus 7 was kind of balanced, right? But now you have lots of, let's say the hydronium would be the hungry lions. You have lots of these hungry lions and not much hydroxide. So as soon as the hydroxide forms, what happens? All these hydroniums want to attack that little bit of hydroxide that forms. Right? And so the population of hydronium and hydroxide from water can never build up to 10 to the minus 7 molar. That's too high of a population to sustain with this much hydronium present. Does that make sense?
Yeah.
And so, in other words, with this high concentration of hydronium here, it prevents the forward reaction from occurring to the same extent as it once did. And now we have a new equilibrium, and the new equilibrium has a much faster reverse rate, and so we don't need much to build up, in other words, to equal. Or should I say much? Yeah. Something like that. And so this is the new. We can't put 10 to the minus 7. It's impossible to generate 10 to the minus 7 molar here. It just isn't going to happen. This is why we had to do the calculation to find out. And it turned out to be 10 to the minus 13. And so let's go ahead and calculate the pH. The pH is going to be negative log of 0.100. And then I need 9 zeros. 1, 2, 3, 1, 2, 3, 1, 2, 3, and then 1. Okay. Which gives me a pH of 1. 1. How many sig figs am I allowed?
2, 3.
3. I'm allowed 3, so it's going to be 1.00. Is that 3 sig figs?
Oh, no.
No. This is not 3 sig figs because we're dealing with a
pH.
power function, and so that means we need another 0. And then a 0 up there just to clear it out. But you might think our simplifying assumption works so well here that did we really have to do this? I mean, in Chem 4, if you calculate pHs in Chem 4, did you ever worry about the water? No, if you're getting 0.100 molar acid, then you just put in 0.100 molar H plus here, right? Have you done pH calculations before? No? And so, in other words, did the hydronium really change that? If we got rid of this 1 out here, would we have gotten the same pH? Yeah. We would have gotten the same pH. And this is why, well, you know, you don't expect much from water. an acid solution. And so this is why, if you did pH calculations in Chem 4, you just ignored the water and just said the pH is the negative log of the acid concentration, and forget the water because the water doesn't really add much to it. Right? That's the Chem 4 style. But if you gave this problem to a Chem 4, if you did this, if you gave this problem to a Chem 4, then they are going to have some trouble. Okay, what is the pH of 1.0 times 10 to the minus 8 molar HCl? Now, the power, it's the power of the hydronium ion concentration. It's the negative power of the hydronium ion concentration. And so a lot of people can do this in their head. They say the pH, the negative power is 8, right? And then figure out how many sig figs. How many sig figs do we have?
2.
2, so it's going to be 8.00. The pH is 8.00. Done. Right? If you know, or you just plug it in. A lot of people just plug it in. This is the negative log of 1.0 times 10 to the minus 8. That's it. Which means what? pH 8 is basic. And so if you add HCl to water, you end up with a basic solution. Yes? I mean, we did the calculation. That's what the calculation is telling us. If you add acid to water, you'll get a base. No, that's got to be maybe that's got to be experimental error, right? Experimental error. Close enough. What do you think?
Forward reaction is going faster.
Forward reaction is going faster. And so there's some other stuff happening that makes pH 8 acid. I mean, there's only acid. Did we add any base? No. And so there's got to be something else. Maybe pH 8 is acid. pH 8 is acid, and then pH 6 must be base? No, that's not right. So somebody tell me what's going on, because a Chem 4 student would be at a loss here because they wouldn't know what to do. I mean, they would have been broadsided. But nobody's going to throw a question like this to a Chem 4 student because they wouldn't be able to handle it. Right? But somebody will throw a question like this to a Chem 1B student because they can handle it. And so how do you handle it? What's the error? What's wrong with this? POH? Power of the hydroxide ion concentration is 8? Yeah. If the POH is 8, we could just change it. Maybe we meant to say POH is 8. Because if you know the relationship between pH and POH, pH plus POH has to equal 14.00 pKw, which we call. And so the POH must be 8, and therefore the pH must be 6. Is that right?
Sounds better.
It sounds better because at least it's an acid. Yeah. Yeah, where is the hydroxide coming from? From the water? Okay. Makes sense.
So what's the answer?
I'm waiting to hear the answer. So think about it some more, because it's not the POH. This is not POH. This is actually pH because it's a lot of people know HCl, the same as hydronium, strong electrolyte, strong acid. It's not because of pOH. What is it because of?
One of the rates of the reactions have changed.
Well, okay. So how does that impact this?
Well, it happened with the other one, so then I figured maybe it happened with this.
Yeah, that's.
Could be the temperature.
You could think of it in terms of rate, or you could think of it in terms of hydronium attacking the hydroxides. No, temperature is the same. This is at 25 degrees C. If no temperature is specified, then you assume it's room temperature. 25.
Okay, how about like water is pH neutral? HCl is pH acidic. That's all.
Okay. Yeah, water would be pH neutral.
So then that's, although whatever that pH is, it doesn't matter, it's always acidic for HCl.
Yeah, I mean, that's along the right track. It's about right. Anybody else?
It's such a small concentration, the scales kind of don't know.
Yeah, it's such a small concentration. It is that it's a very small concentration of HCl, which means what? We'll go back to here. If we have a very small concentration of HCl, what does that mean for this?
You have a large concentration.
Yeah, this is going to grow bigger. And so let's say we're removing a drop or adding a drop to a lake of water. But if we add or remove a drop from, let's say, half a milliliter, you know how many drops are in a half a milliliter? There are only 10 drops in a half a milliliter. And so if we remove one drop from 10 drops, we've just lost 10%. Whereas if we remove one drop from a huge body of water, then the percentage loss or the percentage change is more like 10 to the minus 10%, right? And so all of a sudden, and people were getting there, it's this is wrong because pH measures the total hydronium, not just the hydronium from the acid, but also the hydronium from the water. And so even though that hydronium from water made no impact here, it was so small, the simplifying assumption worked beautifully. Over here, it's different. And so let's take a look at this. And so we're going to set this up as a reset. And so we're going to do all these problems as kind of two-step problems. I'm going to start doing them like this. And so the last problem I skipped a step. Petrucci skips a step. The step he skips is showing the ionization or the hydrolysis of HCl. I'm going to do that. When we do the stepwise, we start with the biggest K. And so here we have this. We have the K for HCl versus the K for water. And when we look at the K for HCl, what does the Ka value tell us? Well, it tells us, how much of this dissociates. And those Ka values can be found on this chart up here. And so find HCl on the chart, and then look up its Ka value, which is, can you see the Ka value? Very large. Do you see it runs from very large to large? There's no number. And so the Ka is very large. Well, we want to start off with the biggest. Very large should be much bigger than 10 to the minus 14. So we're okay. And so initial, we have 0.100 molar, and we think of this as HCl molecules. And this is the dissociated ion. And so we reset this. So we assume no HCl has dissociated yet. And then there's going to be change, and then we'll have some equilibrium. Now, how big is the change here? If we have a K that we don't even have a number for, it just says very large, then you're going to assume that the change is very big. There's going to be a big change because this, we assume, 100% reaction. And so if all of it reacts, we get minus 0.100 molar here, plus 0.100 molar here, plus 0.100 molar here. We don't even need an X because we know what X is already. And so at equilibrium, we're going to have 0 molar here, 0.100 molar here, and 0.100 molar here. So that's what we do when we're given this very large K. Okay, then we go to the next biggest K. And in fact, we only have one more K. That's KW. So that's H2O liquid plus H2O liquid. There's the hydronium and hydroxide. I wrote this as a one-way arrow rather than equilibrium here. Okay, I set it up like this because this is how we're going to do all the problems. Chloride, this is the end of the road for chloride. So chloride's not going to change from here. And the same thing with HCl. Here. But hydronium here doesn't. Hydronium participates in the next step. And so the hydronium we're going to get rid of from here and then bring it over here. And so initially we're going to have 0.100 molar hydronium from the acid. And so water is a liquid, that's a liquid, so we ignore it. And so initial from the acid is 0.100 molar here. How much hydronium are we going to have from water? We're going to assume that 10 to the minus 7 molar. If we assume 10 to the minus 7 molar hydronium and 10 to the minus 7 molar hydroxide from water, that's a Le Chatelier's type setup. So instead of assuming 10 to the minus 7 molar and 10 to the minus 7 molar, we know we aren't going to get that much because hydronium is like a predator, right? We're going to get a lot less. And so what we do is we assume, okay, this is the initial from the HCl, and then the initial from the water. All this spell it out. HCl gives 0 hydroxide. Water, we're going to reset. Remember? 0 and 0. And so the initial combined is going to be 0.100 and 0. And then we continue like we did. So this is the setup for the last problem. The only difference is I inserted this extra step here. Your book just jumps to step 2 right here. But we're going to jump back and do step 1. So this is step 2. This is step 1. Sometimes we can save time. Sometimes we save time by looking at step 2. You look at step 2 and say, you know, is step 2 going to really contribute much hydronium? Do you think that's going to alter the pH much? And then we think, what is the maximum amount? You know, if this were pure water and there were no predators out here, you know, like no large population of predators out here, if this were pure water, then the water molecules can collide, they can react, they'll produce some hydronium and hydroxide, and that population will control itself, right? But now we have lots of predator here, so when we have this reaction, as soon as we start building up a little bit of hydroxide, that hydroxide is immediately taken out or consumed by the hydronium. And so in pure water, we can build up to a concentration of 10 to the minus 7 molar. But when we have a lot of hydronium in there, are we going to get even close to 10 to the minus 7 molar? Not even close. In fact, we got like 10 to the minus 13. A heck of a lot less, right? Because of all this hydronium there. And so sometimes we can go, you know, step 2 is not really going to contribute much because look at that K value. The K is 10 to the minus 14. I really don't expect much. And so sometimes to save time, we just skip eliminate step 2 and then just calculate our pH based on step 1 as a time-saving method. But that time-saving method only comes from doing a lot of these problems, right, and seeing how they work out. And so that would have worked nicely for the previous problem. Just, step 2, did it really add much hydronium? No, it was just like a tiny drop in the big bucket. Tiny drop in the bucket. Nothing to worry about. But here, this is something different. And so this is 1.0 times 10 to the minus 8. A molar initial. This is 0 molar initial. And this is 0 molar initial. And so we'll just proceed as before. So we'll just reset up the problem. Set it up using this new concentration of HCl. What's the change going to be here? Fill out the rest of the table for me. Okay, do we want to say minus x, or do we already know what x is? You should already know what x is. And how do you already know what x is? From the k value. The k says very large. I mean, if you try to look for a number on that, are you going to find a number there? There's no number. This is very large, literally. Very large. Which means we know what the x is. Because we're going to make an assumption. What do we assume? That's just 100%. So I already know what my x is. I don't need to write x. I'm just going to write minus 1.0 times 10 to the minus 8 molar. What's this? Plus 1.0 times 10 to the minus 8 molar. And plus 1.0 times 10 to the minus 8 molar. And so at the end of this, I'm going to have 0 molar HCl. And it's all going to be converted into hydronium and chloride. 1.0 times 10 to the minus 8 and 1.0 times 10 to the minus 8. Okay, now what do? I look. This is the end of the road for the HCl. This is the end of the road for the chloride. But what do I do with the hydronium? The hydronium, what do I do with that?
You bring that value of the hydronium to the water.
Yes. Yeah. I look at the next step. The next step, well, I only have one other thing, and that's water. And so in the next step, I'm going to bring it up here. So I'm going to get 1.0 times 10 to the minus 8 molar hydronium from step 1. And so all this hydronium goes to step 2. How about hydroxide? Do I have any hydroxide? No, because I'm going to reset. There's no hydroxide from step 1, and there's no hydroxide from water. Why is there no hydroxide from water? There should be, shouldn't there? Should have been 10 to the minus 7 molar hydroxide from water, but not anymore, because we're going to reset it. Reset it. In fact, what we say is, well, the water hasn't yet collided. It's not true, but it makes the math easier. We reset it. And so this is our new initial. That's our new initial from both the acid and water. Okay, so this is the initial acid from HCl. And then I'm going to get, what is plus X? Plus X is the additional hydronium I get from water. But the additional hydronium I get from water is not 10 to the minus 7 molar. Why not? Why isn't X just 10 to the minus 7 molar when you get these water-water collisions? The answer is no. Why? It's going to be a lot bigger, a lot smaller, or about the same? It's going to be a lot smaller because, well, hydronium is not a problem. It's the hydroxide, because I can't build up, because these are 1-to-1 stoichiometric ratio. And so I cannot build up much hydroxide because I have too much hydronium present. And so I know it's going to be a lot smaller than 10 to the minus 7. Well, let's see what it is. And so at equilibrium, I'm going to get 1.0 times 10 to the minus 8 plus x molar and x molar. And so the reset means that I have fewer binomials. That's always good. And now let's try to solve for x. Okay, so I know that Kw is equal to the hydronium ion concentration at equilibrium, 1.0 times 10 to the minus 8 plus x, times the hydroxide ion concentration, which is just x, which is equal to 1.0 times 10 to the minus 14. All right, you know, 10 to the minus 14, is that a small k or a big K? That's a really small k, and if you have a really small k, that tells us that the reactants are favored, right? And so do I expect much product formation? Do I expect much reaction here? I don't expect much reaction because the reactants are favored. And so that means might as well try the SA. And that is x is much smaller than 1.0 times 10 to the minus 8. And so we'll try that. This simplifies to 1.0 times 10 to the minus 8 times x. We can't drop the x because anything is significant compared to 0. And so this makes the math a lot easier. X is just equal to 10 to the minus 14 divided by 10 to the minus 8, which gives me 1.0 times 10 to the minus 6. And then we justify this by calculating the percent change. We calculate the percent change. And the percent change is the change 10 to the minus 6 over the initial 10 to the minus 8 times 10 squared. 10. And so this gives us 10 to the 4th percent, which is 10,000% change. 10,000% change is too big, and so it fails. And so that means that this whole thing didn't work. Why did it work in the last problem but does not work in this problem? Did K change? K didn't change. And so why did it fail now? It worked fine last time.
Because Ka is very large.
The Ka was very large in the last problem. So why did it fail this time? And
The concentration of HCl, or
the initial concentration, right. The initial concentration last time was 0.1. And 0.1 is like a huge pool of water. Whereas this one is 0.00000001, which is like a tiny, this is like, so you're taking a drop from a drop. Is that a significant change? Yes. And so in this case it's going to fail because the initial, even though the K is the same, we aren't starting with a big pool of water. We're starting with a few drops of water. And if you take a drop from a few drops, it's going to fail. And therefore, we have to use the quadratic. But fortunately, having fewer binomials means getting this into quadratic form is a lot easier, which is just x squared plus 1.0 times 10 to the minus 8x minus 1.0 times 10 to the minus 14 gives us 0. And then x is equal to 9.51 times 10 to the minus 8. Using the quadratic, and that means that this. When we look at the hydronium, I erased it. I shouldn't have erased it because I was trying to save time, but I ended up taking more time, unfortunately. But at equilibrium, we had 1.0 times 10 to the minus 8 from the HCl plus our x, 9.51 times 10 to the minus 8. And so this is the hydronium from the acid. This is the hydronium from water. And so we end up with 10.51 times 10 to the minus 8 molar hydronium total. This is from acid. This is from the water. Who gave more hydronium, the acid or the water? The water. In fact, if we look at the total, more than 90% of the hydronium in the total came from water. Less than 10% came from the acid. And so in this case, we cannot ignore that contribution. And the hydroxide is going to be 9.51 times 10 to the minus 8 molar. And then we've got to check these two concentrations to make sure it works. But it does. You know, this checks out 2K equals 1.0 times 10 to the minus 8. 14. So that checks. And then the pH, let me just finish with this. I know I'm out of, we're done. So over time here, sorry. Okay, I'll stop here.